In this lecture, I'm going to discuss some features of subsets called being open, closed, or bounded subsets. So in one variable calculus, we had some very important types of subsets. So AB, we have these closed intervals as well as open intervals. So this consists of all numbers between a and b, where in the first case we include a and b, and in the second case we exclude them. So this is all x in R with a less than equal to x less than equal to b, and here it's strictly less than. And there's also these half-open intervals like this, but these are not as useful. Anyway, so we want to have a version of these in higher dimensions. So first, let me rewrite this slightly. I'm going to rewrite a b as this is x minus epsilon, x plus epsilon, where x is the average of a and b, and epsilon is, this is, that's right, is their difference. So the interval from a to b is centered at x, and I'll say has radius epsilon. So now in higher dimensions, we define the following. So if x is a point in Rn, such as three-dimensional space, and epsilon is a real number, then we define the closed ball of radius epsilon centered at x is, so I won't really use this notation that much, but it's helpful to have here. So this is going to consist of all points y such that the distance, vector distance of x minus y is less than or equal to epsilon. So, and I'll also call this sometimes a disk. So in two-dimensional space, this could be like this filled-in disk here. Then we define the open ball, or disk, especially if we're working in two-dimensional space, of radius epsilon centered at x is, now we take all points y where the distance between y and x is strictly less than epsilon. So this will look like, this is x, it'll consist of all points inside this circle, but not the points on the edge or boundary, which we're about to define precisely. And then the sphere of radius epsilon centered at x is, this could be written SRX, or sorry, S epsilon x, and this is all y, such that distance from y to x is exactly epsilon. So, so the closed disk, the closed ball is equal to the open ball union the sphere. Again, we're not going to use these notations throughout the course, but it's helpful for introducing the concepts. So for instance, if we look at the function fxy equals ln of 16 minus x minus 1 squared minus y plus 2 squared, and we want to know the domain of f, well, we see that we need x minus 1 squared plus y plus 2 squared to be less than, strictly less than 16, since we can't take ln of a negative number. And so this is exactly the disk, the open ball of radius 4 centered at the point 1, -2. So this gives us a way to describe, or some language to describe the domain of f. Now I want to consider more general regions of space. So let R be a region in Rn, so I mean a subset. So maybe in R2 we have this this is sort of lumped as a subset of the plane. And actually, let's say here it doesn't contain these points. So now if we have a point x in R, or just a point x, we say that so x, which is contained in R, is an interior point of R if it is the center of a, here you could take solid or of a ball entirely contained in R. So here we could take this is entirely contained in R. So this x is an interior point. If we took our instead x to be, say, a point like right here, then it's still contained in a ball of some radius. We just have to be more careful about the radius. This is going to be very, very, very small radius, whereas some of the points, a point outside of R is not an interior. And if we take a point here, this is in R, but there's no disk that's small enough to be contained entirely within R. And so then our next definition is x is in the boundary of R, which we sometimes denote backwards 6R, or partial R, if every ball centered at X contains both points contains points in R and points not in R. So this has nothing to do with X. This gives us a way to make precise the idea of this edge of the shape. So yeah, any point on here. And note for this definition, X doesn't have to be in R. So yeah, the boundary, the points on the boundary, every ball around them contains both stuff inside of R and stuff outside of R. Then we say that R, the subset, the region itself, R is an open subset if every point of R is an interior point. So you always have some wiggle room. Whereas R is a closed subset if it contains its boundary. So if every boundary point is contained in R. Or using the notation that I did over there, if and only if R, boundary of R is contained in R. Whereas, so something is closed if it contains all its boundary points. Something is open if and only if it doesn't contain any of its boundary. Or if you like in notation, boundary R intersect R is empty set. So we think of open subsets as being drawn like this, closed subsets as being drawn like this, and the subset I've drawn here, this is neither open nor closed, since it contains some of its boundary points, but not all of them. Now, one more definition. So I will say that R is bounded if it's contained in some ball. So it doesn't stretch off to infinity, and is unbounded if not bounded. So this might seem a little silly to spell that out, but just as a warning, R is open if and only if the complement Rn minus R is closed. So open does not mean not closed. It means the complement is open. All right, so for example, if we were looking at the region y greater than or equal to x squared, so that is, we draw in the plane, that'll be everything above here. This is a closed subset of the plane, but it's not bounded.